Paper 1, A-Level Chemistry, June 2017. Give the term enthalpy of lattice formation, question 1. So this is the enthalpy change, the energy change, when 1 mole of a solid ionic lattice, try and use the word solid ionic lattice in there, is made from its gaseous ions. So when, say for example, Ag plus gas and I minus gas make AgIs as a solid ionic lattice. Use the data to calculate the enthalpy of lattice of formation of silver iodide. Well, what I'd do first of all to try and help me is try and write the enthalpy of lattice formation equation. So lattice formation, as we've said, is the gaseous ions coming together, 1 mole of them to make 1 mole of a solid, 1 mole of an ionic solid lattice from its gaseous ions. So we should be able to work out the lattice of formation equation. And then what we do is we use these and piece this together. Have we got anything with Ag plus in it? Yes, we have. We've got Ag plus here going to Ag plus gas going to Ag plus AQ, Ag plus gas going to Ag plus IQ. So we've got this coming down to Ag plus AQ. And it tells us the enthalpy change is minus 464. Have we got anything with I minus gas in it? Yes, we have I minus gas coming to I minus AQ. So we've got that equation, I minus gas coming down to I minus AQ. And we've got the enthalpy change is minus 293. Have we got anything with AgI solid in it? Yes, we have. AgI solid going to Ag plus AQ and I minus AQ. We've got that, and we know the enthalpy change for that is plus 112. Now, how are we going to link these together? Ag plus AQ going to Ag plus AQ here. Here to here is nothing because it's the same thing. I minus AQ going to I minus AQ from here to here is nothing because it's the same thing. So if I come through from here round this way, a process called Hess's law, where the enthalpy change is independent of the route taken, and instead of going straight across from here to here, I can come round here and I can come round here, and then I can go up this way. I'm going down in the right direction. I've got the right number of particles, so I've got a minus 464 and I've got a minus 293 to make these. Across here is nothing, and then I've got to reverse this sign to come back up here to here, so it's a minus 112. So it's a minus 464, minus 293 and a minus 112. I'll reverse this equation round, minus 869 kilojoules per mole. The calculation of enthalpy of lattice formation of silver iodide based on the perfect ionic model gives a smaller numerical value than the value calculated. So what's the perfect ionic model to start off with then? The perfect ionic model assumes that there's no covalent bonding. So if it doesn't match, the AgI must contain some covalent bonding. We sometimes call that covalent character or covalent bonding. It's got to contain some covalent bonding. The model assumes that everything is all ionic, 100% ionic, and the fact that it's different must mean that it's not 100% ionic. There must be some covalent character or covalent bonding in there. And in actual fact, because the value in the model is less than the actual value, it means that the bonds in the lattice are actually stronger than in the model because you're getting more energy given out, so it's more exothermic. So if it's more exothermic, then it's going to end up with more stable product, and the bonds are stronger than expected. Identify a reagent that could be used to indicate the presence of iodide ions. So you're using silver nitrate in acid, preferably in nitric acid, silver nitrate in nitric acid, and the observation is that you're going to get a yellow precipitate. Incidentally, if you wanted to check that the precipitate was yellow and it was silver iodide as a yellow precipitate, that you got iodide ions and you made silver iodide rather than silver bromide or silver chloride. Silver chloride is white, and it will dissolve in dilute ammonia. Silver bromide is cream and it will dissolve in concentrated ammonia. Silver iodide is a yellow precipitate and it won't dissolve in even concentrated ammonia. So that's a check to make sure that you actually have got the colour does, which is the colour sometimes difficult to tell between yellow, cream and white sometimes, so the use of ammonia will just be a double check to make sure that you've got iodide ions rather than possibly bromide or chloride ions there. The nitric acid in there, the acid is stopped the formation of silver carbonate, which is a precipitate as well, because the acid would dissolve the carbonate and stop silver carbonate forming as a precipitate. Question 2 is about buffers. So I've got a acid dissociation constant and equilibrium constant for an acid for ethanoic acid. So ethanoic acid is breaking up to make CH3COO- and H+. And I've been given the expression for the acid dissociation constant Ka, the equilibrium constant for ethanoic acid. I've been given a value for it, a buffer solution with a pH of 3.87. So why have I been given 3.87? The reason I've been given 3.87, pH of 3.87, the only reason is because pH is minus log to the base 10 of hydrogen ion concentration. They want me to use the pH to work out H+ concentration. So that's the first thing that they want me to do. So if pH equals 3.87, so minus log to the base 10 of hydrogen ion concentration pH equals 3.87. Then what I do is I minus both sides so that log H is minus 3.87, and then I can inverse log or shift log or second function log, find the right button on your calculator, of 3.87 to find the hydrogen ion concentration. It comes out as 1.3489 times 10 to the minus 4. So now I've got the hydrogen ion concentration. A buffer solution, in the buffer solution, the concentration of ethanoate ions, that's those on the top, was 0.136. I've got to work out the concentration of ethanoic acid on the bottom, so I've got all the values I need now. So I've got 1.74 times 10 to the minus 5 is the acid dissociation constant, equals 0.136, which is the concentration of ethanoate ions, which I'm given in the equation. Hydrogen ion concentration I've just worked out, divided by the concentration of ethanoic acid. So that's the concentration of ethanoic acid on the bottom. It should have square brackets around it really. And so concentration of ethanoic acid is 0.136 times 1.3489 times 10 to the minus 4, which comes out as 1.83 times 10 to the minus 5, divided by 1.74 times 10 to the minus 5, and the concentration is 1.05 mole per decimeter cubed. I've put 3 significant figures because everything else in the question is to 3 significant figures. In a different buffer solution, the concentration of ethanoic acid was 0.25 mole dm to the minus 3, and the concentration of ethanoate ions was 0.121. Some sodium hydroxide was added to 500 centimeter cubed of this buffer solution. So I've got the volume of each of volume, and I've got the concentrations of ethanoic acid, and I've got the concentrations of ethanoate ions. So if I've been given concentrations and volumes, then I can work out the number of moles of ethanoic acid and ethanoate ions. So for ethanoic acid, concentration is moles divided by volume, so 0.0260 is the number of moles divided by 0.5, so I've turned 500 centimeter cubed by dividing it by 1000 into decimeter cubed, 0.5, and so I've worked out the number of moles of ethanoic acid is 0.13. I've done the same for sodium ethanoate, so concentration 0.121 is the number of moles divided by the volume, which is the same volume because it's the same solution, 500 centimeter cubed or 0.5. 0.121 times 0.5 is 0.0605. So I've got the number of moles of each of them in this buffer solution. I've added some sodium hydroxide, and it tells me that the amount of sodium hydroxide, it's given me the number of moles, 0.007 moles. Now what the sodium hydroxide does is it reacts with the acid. So the sodium hydroxide will react with the acid. So because this is an alkali or a base, sodium hydroxide will react with the acid. So instead of being 0.13 moles, some of the sodium hydroxide, 0.007 moles of this, have reacted with some of this. So the amount of ethanoic acid that I've got left is what I started with, 0.13, take away 0.007 because the sodium hydroxide is reacting. It reacts 1 mole of sodium hydroxide reacts with 1 mole of ethanoic acid, so 0.007 moles of sodium hydroxide will react with 0.007 moles of ethanoic acid. So 0.007 moles of ethanoic acid have been used up. So the amount remaining is what I started with, 0.13, take away 0.007 is 0.123. Now when it reacts, what does it make? Well, it makes something called sodium ethanoate. It makes ethanoate ions. So sodium ethanoate started off with 0.0605 moles of sodium ethanoate. When the sodium hydroxide reacts with the ethanoic acid, it makes sodium ethanoate. It makes more of these. So it actually adds on 0.007 moles of sodium ethanoate because 0.007 moles of sodium hydroxide react with 0.007 moles of the ethanoic acid to make 0.007 moles of sodium ethanoate, so we need to add that on. We add those two together and then we put in all of the numbers, we work out H plus and we work out pH, and pH will turn out to be 4.50 to 3 significant figures. I've put a 0 on there because everything else is to 3 significant figures. Question 3. Question 3.1. Which is the correct expression for Kw? That's just something to learn. Kw is the H plus concentration multiplied by OH minus concentration. The answer is C. Calculate the pH of pure water at 10 degrees C. Give your answer to 2 decimal places. Well, Kw is H plus multiplied by OH minus concentration. If I have a water molecule dissociating, breaking up, then for every H plus particle I make, I'm going to make one OH minus particle because they've come from the water molecule being dissociated. So H2 makes H plus plus OH minus. So every time one of those is made, one of these is made. So H plus concentration has got to equal OH minus concentration. So instead of H plus multiplied by OH minus concentration, I can replace the OH minus concentration with H plus. So Kw is H plus squared. Kw equals 2.93 times 10 to the minus 15, so H plus squared is 2.93 times 10 to the minus 15, so H plus concentration is the square root of that, 5.41 times 10 to the minus 6. I do minus log to the base 10 of that, because minus log to the base 10 of hydrogen ion concentration is pH, minus log to the base 10 of 5.41 times 10 to the minus 6, 7.27. Don't worry that it's not 7 exactly. Temperature, changing the temperature can alter the pH of water. Suggest why this pure water at 10 degrees C is not alkaline. Well, it's only alkaline if I've got more OH minus than I have H plus. So if I've got an excess of OH minus, it's going to be alkaline. If I've got an excess of H plus, it's going to be acidic. So the fact that I've got equal concentration of H plus and OH minus means that it's not alkaline. Just because its pH is not 7 doesn't mean that it's just because it's higher than 7 doesn't mean that it's alkaline. That just means that I might have changed the temperature. I might have added some alkali, but I haven't. I've just changed the temperature. That's how I've altered the pH. So the fact that H plus concentration equals OH minus concentration because it's pure water means that it's not alkaline. Calculate the pH of 0.031 solution of calcium hydroxide. Well, calcium is in group 2, so calcium's in group 2. If calcium's in group 2, it forms Ca2+. It forms a 2+ ion. It loses 2 electrons, and a hydroxide ion is a -1. So calcium hydroxide is CaOH2. It's got to have, because 2 pluses needs 2 minuses to balance out. So every time 1 mole of calcium hydroxide dissolves, it makes 2 moles of OH minus. So I've got to multiply the OH minus concentration is twice the concentration of the calcium hydroxide. So it says calculate the pH of a 0.031 mole solution of calcium hydroxide. So if the calcium hydroxide solution has got a value concentration of 0.131, then the OH minus that's made when it dissolves, when the calcium hydroxide dissolves, I make 2 moles of OH minus, so it needs multiplying by 2, 0.0262. Now then, I've got OH minus. I need H plus if I'm going to work out pH. So Kw equals H plus OH minus. That's why they've got you to do that in the first part of the question. Kw is 2.93 times 10 to the minus 15 from the first part of the question. H plus we don't know, OH minus we've just worked out, so H plus is 2.93 times 10 to the minus 15 divided by 0.262. I've worked out H plus concentration minus log to the base 10 of it, and it comes out as 12.9514, and I'm going to put it to, I should really put it to 3 significant figures, because I've got 3 significant figures here, so it should be 12.9 or 13.0. The 0.0131 solution of calcium hydroxide is a saturated solution. If I'd used magnesium hydroxide instead at the same concentration, with the pH would be larger or smaller. Well, magnesium hydroxide is less soluble. As you go up group 2, the magnesium hydroxide, the hydroxides become less soluble. So magnesium hydroxide is less soluble than calcium hydroxide, so less of it's going to dissolve, and therefore the pH is going to be smaller because magnesium hydroxide is less soluble than the calcium hydroxide. So it's a question about solubility. Question 4. A sample of titanium was ionized by electron impact in a time-of-flight mass spectrometer. Information from the mass spectrum about the isotopes of titanium in the sample shown in Table 2. So mass divided by Z, that's mass divided by the charge on the atoms, or the ions now. So the atoms are ionized and they lose 1 electron, so they become +1 charge. So mass divided by +1, mass divided by 1 is just the mass. So these are the masses of the atoms in titanium. Why does titanium have atoms of different mass? Well, they're all titanium because they've all got the same atomic number or proton number. They've all got the same number of protons and electrons, but they've got different numbers of neutrons. That's why they have different masses. They're called isotopes. And this is the percentage abundance. So 9.1% have got mass 46, 7.8% have got mass 47, 74.6 have got mass 48, and 8.5% have got mass 49. So if you imagine you had 100 particles, 9.1 out of the 100 have mass 46. So their combined mass is 9.1 times 46, 418.6. And you can do the same for the others. 7.8 out of the 100 have mass 47, so their combined mass is 366.6. 74.6 out of the 100 have mass 48, so their combined mass is 3580.8. And 8.5 out of the 100 have mass 49, so 8.5 times 49 is 416.5. So the total mass, if you add them all up, the total mass of all of the 100 particles altogether is 4782.5. The average is the total mass, 4782.5, divided by the number of particles, divided by 100, is 47.8. It requests it to 1 decimal place, and we've given it to 1 decimal place, 47.8. So, write an equation including state symbols to show how an atom of titanium is ionized. So you've got Ti, and it's a gas. It's got to be a gas. So going into the time-of-flight mass spectrometer, it's a gas, and then an electron is removed from it, so it becomes Ti+. Again, it's still a gas. So including state symbols, they're all gases. MZ value of the ion that would reach the detector first. So the one that's going fastest would reach the detector first. The one that's going fastest has got the smallest mass. So 46, titanium with a mass of 46, that atom would reach the detector first. 49 would reach it last because that's the heaviest. Calculate the mass in kilogram of 1 atom of titanium. And you give them the Avogadro's constant. So the average mass of 1 mole we've now worked as 47.8. We know the number of particles in a mole is 6.022 times 10 to the power 23. So it's 0.047 kilograms. So to convert grams into kilograms, you divide by 1,000. So a small unit going into a larger unit, divide by 1,000. So it's 0.047 kilograms. It requests in kilograms, divided by the number of particles in there, will give you the mass of 1 particle in kilograms. In a time-of-flight mass spectrometer, the time-of-flight T is given by this equation, where D is the length of the flight tube, M is the mass of the particle in kilograms of going down the tube, and E is the kinetic energy of the ions. So the things that aren't going to change, the distance, though the length of the tube is not going to change, so D is going to stay the same, and E, the kinetic energy of the ions. The kinetic energy of the ions put into the tube is always the same, irrespective of what kind of ion you put in there. So E is going to stay the same, so 2 lots of E are going to stay the same. So D and 2 lots of E are all going to stay the same for each of the ions that are put in there. So we've said that already. D, so I've rearranged this equation. I've taken square root of m divided by 2e. From the top on this side, I've taken it across the equal sign, it goes onto the bottom. So D is 2 divided by the square root of m over 2e. And so the distance, or the length of the tube is going to be the same. So this value, T divided by the square root of m over 2e, is going to be the same for whichever ion you've got. So for 49 titanium Ti and 47 titanium Ti, then T divided by square root of m over 2e is the same for each. And I've even cancelled 2e as the same on each side as well. So 2e is going to be the same on this side. So T divided by square root of m over 2e is the same as T divided by m over the square root of m over 2e on the right hand side. I've cancelled the 2e on each side because 2 lots of E, 2 lots of the kinetic energy are the same for each particle. So now I've got the time divided by the square root of the mass of the particle equals the time for this to reach the detector, 47 Ti, divided by the mass of this one. The masses are 49 and 47 respectively, so T divided by the square root of 49 equals T divided by the square root of 47. The times are different, of course. The time for 49 Ti is given as this value here, so 9.816 times 10 to the minus 7 divided by the square root of the mass of the particle 49 is time taken for the 47 Ti to hit the end of the tube, the detector at the end of the tube, divided by its square root of its mass, 47. So I've multiplied both sides by square root 47, and so T, the time for 47 Ti equals 9.612 times 10 to the minus 7. Question 5 is about entropy and Gibbs free energy change. So we've got some entropy values for each of these substances here, and we've got an equation. Use the equation to calculate Gibbs free energy change and then explain why the reaction is feasible. In other words, if it's 0 or less than 0, 0 or negative. So let's have a look then. So for entropy change, the entropy change is the sum of the entropy of the products, the entropy of these on the right hand side, take away the sum of the entropy of the reactants. So entropy change is this one, 2 moles of CO, so 2198, 1 mole of titanium chloride, which is a 253. Subtract the sum of the entropy of the reactants, so that's subtract a TiO2, which is a 50.2. Subtract, I've got 2 moles of carbon, so 2, subtract 2 5.7s, and subtract 2 223, because I've got 2 moles of Cl2. I can calculate delta S then, but that's in joules per Kelvin per mole. And it needs to be in kilojoules. The reason it needs to be in kilojoules is because in a minute I'm going to use Gibbs free energy change, so delta G equals delta H minus T delta S, and delta H is in kilojoules, so I've got to get this in kilojoules. So I'm going to divide by 1,000 to get joules into kilojoules, a small unit value into a larger unit value, I divide by 1,000. And now delta G equals delta H minus T delta S. So delta H is minus 60, and I've got them both in kilojoules now. Kilojoules and kilojoules for delta H and delta S. Temperature. Now temperature is given in degrees C, and it needs to be in Kelvin. So this temperature is in Kelvin. So I'm going to take 298, I'm going to add 273, and I'm going to multiply by my 0.141, which is my entropy change. Delta G, therefore, is minus 238. I'm going to put it to 3 significant figures because everything else in the question is to 3 significant figures, and whether it's feasible or not, well, if delta G is 0 or less than 0, negative in other words, then it's feasible and going to go ahead. Question 6 is about some period 3 elements and their oxides. Write an equation for the reaction of phosphorus with an excess of oxygen. Well, you need to know that phosphorus is P4 and P4O10 is phosphorus oxide. So you could probably work that out, that phosphorus is in group 5, so it's got an oxidation state of 5, 4 5s are 20, oxygen's in group 6, gains 2 electrons, oxidation state 2, 10 2s are 20, so that balances out the oxidation state to leave no charge overall, and you can need 5 O2s to balance the 10 O's. That might be something to learn. Describe a test you had used to carry out to distinguish between sodium oxide, which is a white solid, and the product P4O10, which is another white solid. Well, sodium is a metal, so metal oxides tend to be basic alkalis, and P4O10, P is a non-metal. Phosphorus is towards the right of the group of the table in group 5. So that's a non-metal oxide, so they tend to be acidic. So you dissolve in water, add a universal indicator. Sodium oxide is going to go blue or purple. And phosphorus oxide is going to go red because it's acidic. So non-metal oxides, elements on the right hand side of the periodic table, non-metals, their oxides are acidic and will turn universal indicator red. Metals on the left hand side of the periodic table in group 1 and group 2 will form alkaline or basic oxides and turn universal indicator blue or purple. State the type of crystal structure shown in silicon dioxide. Well, silicon dioxide, sometimes called silica, is the main constituent of sand, and it's got a large macromolecular structure, a giant covalent or a macromolecular structure, a bit like diamond, where it's all held together by strong covalent bonds. Sulfur trioxide, well, in a warm room it's a gas. At around about 46 degrees C, it's actually boiled and turned to a gas. So sulfur trioxide is molecular with van der Waals bonds holding it together. So the SO3 molecules, and then they're held by van der Waals bonds, intermolecular van der Waals bonds. So it's a molecular structure. Explain why silicon dioxide has a higher melting point than sulfur trioxide. I think I've already explained that. Many strong covalent bonds are actually in the structure of SiO2. So held in a large giant covalent structure or macromolecular structure, so covalent bonds between all of the atoms, weak van der Waals bonds between the molecules in SO3, and therefore the covalent bonds are stronger than van der Waals bonds, more energy to break them. Write an equation for the reaction of sulfur trioxide with potassium hydroxide. So sulfur trioxide is SO3, potassium hydroxide is KOH, and then if you just put everything together, SO3 plus KOH makes potassium hydrogen sulfate, KHSO4. So you just look and see that, just balance it up with 1K, 1H, 1S and 4 O's, or you can balance it this way as well. You can actually make some potassium sulfate. Hard to try the formula of potassium sulfate. You've got to know that an SO4 is an SO4 2- ion. You could probably work that out. Sulfur's in group 6, oxidation state +6. Oxygen's 4 -2s because oxygen's in group 6 with a -2 oxidation state. 4 -2s and 1 + 6 is a 2-. 2- potassium is in group 1 +1 oxidation state, so you need 2 +1s to balance out the 2- of the SO4 2- ions, 2 KOH and some water as well. But the top equation is easier to balance. Write an equation for the reaction of excess magnesium oxide with phosphoric acid. So phosphoric acid is H3PO4. So a phosphate ion is a 3- ion, so you're going to need, that's in oxidation state 3- is a PO4. Again, you could have worked that out with phosphorus in group 5, 4 -2s is -8, so -3, hydrogen in +1, so I'm going to need 3 of those to balance up the 3- on the phosphate ion. MgO, 2+ and 2-, so it's just MgO, oxidation state +2 and -2 for the oxygen in group 6. And therefore, you know, if that's a 3- and this is 2+, you're going to need 3 2+s to balance out the 2 3-, and then balance up the waters with the oxygens. Draw the displayed formula of the undissociated acid when sulfur trioxide reacts with water. So you've got SO3 and H2O, so SO2 and SO2 and H2O is going to make H2SO3, not sulfuric acid, but something called sulfurous acid, and it looks like that. Sulfuric acid, it looks like that. You'll probably know that from paper 2, from your organic reactions, your electrophilic addition, and SO3 looks like. Solution A contains the compound CuH2O6Cl2. So what's going on here? We've got a complex ion CuH2O6, and copper is in +2 oxidation state. It's got a 2+ charge. So this CuH2O6 has got a 2+ charge, and it's got 2 Cl- ions, 2 chloride ions attached to it as well. State the type of bonding between the oxygen and hydrogen in this compound. We've got waters in there, so the bonding between the oxygen and hydrogen is a covalent bond. State why the chloride ions in this compound are not considered to be ligands. Well, they're Cl- ions just attracted to the CuH2O6 2+. There's ionic bonding going on between the Cl- ions and the 2+ CuH2O6 2+. Actually, a ligand is a lone pair donor, so it forms something called a coordinate bond or a dative bond, and it's a lone pair donor. The Cl- is the chloride ions and not lone pair donors. An excess of ammonia was added to a sample of solution A to form solution B. So what actually happens is that 4 of the NH3s, 4 of the ammonias, replace 4 of the waters. 2 will remain. So we've got CuH2O6 2+, and 4 ammonias replace 4 of the waters. 2 remain. It's still 2+ because NH3 and H2O have got oxidation states of 0. They've got no charges. So the 2+ still remains and 4 of the waters come off. The colour is a deep blue solution. You can also say a royal blue or a dark blue solution. Any of those will get the mark. An aqueous sodium carbonate was added to another sample of solution A. So to form a blue-green solid C. So A is copper, so it's going to make copper carbonate, sodium carbonate, and this copper complex will make copper carbonate, a blue-green solid. Reagent D was added to another sample of solution A to form a yellow-green solution. So this forms a yellow-green solution, which is actually CuCl4 2-. So to replace the waters with Cls, you're going to have to use concentrated hydrochloric acid. And concentrated hydrochloric acid will replace those 6 waters with 4 Cls. So 6 of the waters, 4 Cl- chloride ions, make CuCl4 2-, 6 H2O. Why only 4 Cls? It's because they're larger than the H2O ligands, and only 4 Cls can fit around the Cu metal ion. So only 4 Cls can fit around the Cu 2+. Now then, why is it 2+ going to 2-? Well, waters have no charge. The Cu has a 2+ charge. If the Cu has a 2+ charge here, and the Cls have a minus charge each, they're in oxidation state -1. They gain 1 electron. They're in group 7. 4 1- is 2+. Leave 2- left over. Or you can look at the fact that 2+ and 4 1- is 2- on the left-hand side, 2- on the right-hand side. Explain why colorimetry cannot be used to determine the concentration of solutions containing CuCl2-. Well, colorimetry is used to test for coloured ions, usually transition ions. And transition ions are usually coloured because they've got incomplete 3D shells. So if you've got an incomplete 3D shell, so a 3D shell that's not full, then they'll absorb visible light. This must have a full D shell because it's not absorbing any light, it's not turning into a coloured ion. So colorimetry, which is measuring the colour of the solution, cannot be used to determine the concentration, how much colour is in this solution. This solution must be colourless, and the reason it's colourless is because it's got a full D shell that cannot absorb visible light. Question 8 is about ion testing for ions. Describe how a student could distinguish between aqueous solutions of potassium nitrate and potassium sulfate. So how do you test for a sulfate ion? You use something called barium chloride, and it makes barium sulfate, which is a white precipitate. Barium sulfate, incidentally, is used in barium meals. It's a white solid then that goes into the tissues, usually of your gut, when you want your gut or your intestine X-ray, because the white solid then shows up in the X-ray. So barium sulfate is a white solid. The reagent is barium chloride. Barium chloride, no change with potassium nitrate. It's not going to make barium sulfate with that, but it will make barium sulfate with potassium sulfate as a white precipitate, or a white solid, you could put. Describe how the student could distinguish between aqueous solutions of magnesium chloride and aluminium chloride using one simple test tube reaction. He'd add something like sodium hydroxide and make magnesium hydroxide and aluminium hydroxide. Magnesium hydroxide is a white solid, a white precipitate or a white solid, either will do. And what you actually get is you get aluminium hydroxide, and that redissolves when you add more sodium hydroxide. So you get a white solid or a white precipitate, either will do, white solid, white precipitate, and in excess, so when you add more sodium hydroxide, then it dissolves. Question 9. There are several stages in the industrial preparation of methanol from methane, and we can see the percentage conversion of methane, so we can see the efficiency of the reaction here. So it looks as if more methane is converted into methanol. So methane into methanol, more and more is converted as the temperature goes up. However, it does seem to drop off a little bit, so we don't seem to get much increase in percentage conversion after around about 850 degrees C. So between 850 degrees C and about 900 degrees C, there doesn't seem to be so much more percentage conversion of the methane into methanol. And here, as the pressure decreases, then less and less methane is converted into methanol. So to deduce the optimum conditions, so what I would suggest is you do using a higher temperature, because as you increase the temperature, the percentage conversion of methane into methanol, methanol is what you want, what you're trying to make, increases. However, I wouldn't go above about 850 degrees C, because beyond that point really you're not getting much more of an increase in percentage conversion. So around about 850 degrees C. As you increase the pressure, the percentage conversion decreases. So you'd recommend a low pressure, maybe about 1000. However, I'd be tempted to use a slightly higher pressure, maybe a compromise pressure, because at a very low pressure, these are gases, and so at a very low pressure the particles are going to be far apart. You want to bring them closer together so that they have a greater chance of having successful collisions, so they have more collisions. So I'd probably recommend maybe 1000 or maybe even 2000 kilopascals. So let's have a look at the answer. Yield increases as temperature increases. Yes. After a certain temperature, the yield no longer increases. Yes, that temperature looks to be about 850 degrees C. Yield decreases, so the yield or the percentage conversion, same thing, decreases. The pressure increases. Yes. High temperature is expensive. So yes, you could put that. After a certain temperature, the yield no longer increases. So therefore, there's no gain in using a very, very high temperature like 900 degrees C. And the optimum temperature, the best temperature, looks as if it's somewhere around about 850 degrees C. A lower pressure is advisable, however it may be too slow. The reason it's too slow is because the particles will be further apart at a lower pressure, and therefore you get fewer successful collisions. So a compromise, some kind of compromise pressure is required, and we said probably the best pressure is 1000, maybe 2000, somewhere around here, just to try and increase the pressure a little bit and bring the particles closer together so that therefore they have more successful collisions. 9.2, we're going to lay this out in a table. It's an equilibrium. So we've got carbon monoxide and 2 moles of hydrogen making methanol, and we've got the amount of number of moles of carbon monoxide in the mixture at the start, and at equilibrium it tells you how much methanol. So let's lay it out as a table as normal. We've got carbon monoxide, we've got H2, and we've got the methanol. At the start we've got 20.1 moles of carbon monoxide, we've got 24.2 moles of hydrogen. We haven't got any methanol, it doesn't tell you you've got any methanol, so we'll have to assume at the start there's no methanol in the mixture, we've not made any yet. 2.16 moles of methanol are made at equilibrium. So at equilibrium 2.16 moles of methanol are made. So how much carbon monoxide is used up? 1 mole of carbon monoxide makes 1 mole of methanol. So I've made 2.16 moles of methanol. I must have used up 2.16 moles of carbon monoxide. For every mole of carbon monoxide used up, 2 moles of hydrogen are used up, so I must have used up double that. 2.16 times 2 is 4.32, and now I can work out how much I've got then at equilibrium. 20.1 moles of carbon monoxide at the start, 2.16 at the end. Subtract the 2 and it's 17.94. I'm going to put it to 3 significant figures because everything else is at 3 significant figures. 24.2 take away 4.32, so I've started off with 24.2 moles of hydrogen. I've used up 4.32. I've got 19.88. Again to 3 significant figures, so I'm going to round up to 19.9 or to 1 decimal place, whichever you prefer. 3 significant figures is easier to understand. And then in the end at the mixture I've got 2.16. I don't know why that says 2.15. 2.16 left at the end in the equilibrium mixture of methanol. Amount of carbon monoxide 17.9, moles of hydrogen 19.9. Okay, a partial pressure question. So what you do for partial pressures are you look at how many moles of each of the gases. A partial pressure is a bit like a concentration, so you work out the fraction of the number of moles. So I've got 2.76 moles of carbon monoxide, 2.51 moles of hydrogen and 0.36 moles of methanol. So add up the total number of moles and I'll work out the fraction of the total number of moles that are carbon monoxide. So first of all, I'm going to add up the total number of moles of gases that I've got. I've got 2.76, add 2.51, add 0.36. I've got 7.63 moles. And then what I work out is what fraction of those 7.63 moles are actually carbon monoxide. So that's 2.76 moles out of the 7.63 moles, which equals 0.362 moles of carbon monoxide. Then I do the same for hydrogen. What fraction is hydrogen? Well, 4.51 moles out of the total of 7.63 moles of gas altogether. That equals 0.613. That's the fraction of gas that's hydrogen. What fraction of the gases are methanol? I've got 0.36 moles of methanol out of 7.63 moles of gases. I've got 0.0472. That's my mole fraction, the fraction of the gases that are methanol. The total pressure is 630. Now, each of these all together, all of the gases, contribute towards a total pressure of 630. Remember, pressure comes from particles colliding with surfaces. So altogether these gases make a pressure of 630. So what pressure comes from this comes from the carbon monoxide? Well, the fraction of carbon monoxide in the mixture is 0.362. So I'll multiply 0.362 by 630, 228 kilopascals out of the 630 have come from carbon monoxide. What's the partial pressure of hydrogen? That should say hydrogen there, partial pressure of hydrogen. Well, I've got 0.613 moles. That's the fraction of the gas that in the mixture that's hydrogen. Out of the so what fraction of the 630 kilopascals comes from hydrogen? I'll multiply 0.613 by 630. 372 kilopascals comes from the hydrogen, and then the partial pressure of the methanol, that should say CH3OH, methanol here. I've got 0.0472. That's the fraction of the gas in the mixture that is methanol, and so out of its contribution to the 630 kilopascals, multiply these two numbers together, 29.7 kilopascals of pressure come from the methanol. Now, my Kp here, I've been given an expression here for the Kp. So it's similar to a Kc. So what you do is you put the partial pressure of the methanol, which appears on the right of the equation here, partial pressure of the methanol divided by the partial pressure of the carbon monoxide divided by the partial pressure of hydrogen squared. It's very, very similar to producing a Kc. Instead of concentrations, you've got partial pressures. So my Kp is the partial pressure of the methanol divided by the partial pressure of the carbon monoxide divided by the partial pressure of the hydrogen squared. It's a squared because there's a 2 here, just like it would be if you're writing a Kc. So now I put the partial pressures. Partial pressure of the methanol, there should be methanol here at the bottom, is 29.7, divided by the partial pressure of the carbon monoxide. The carbon monoxide is the top one, 228, and then I've got partial pressure of hydrogen, that's that one, 372 squared, 9.41 times 10 to the minus 7. What are the units? Well, I've got a unit of pressure, kilopascals on the top, I've got kilopascals on the bottom, and I've got 2 more kilopascals on the bottom. So I've got 1 kilopascal on the bottom, and I've got 3 kilopascals, sorry, 1 kilopascal on the top, 3 kilopascals on the bottom, so I've got 2 kilopascals on the bottom. So when I cancel 1 kilopascal on the top and 1 kilopascal on the bottom, I end up with 2 kilopascals on the bottom. So it's 1 divided by kilopascal, kilopascal, or kilopascal to the minus 2. Question 10. Table 4 shows some electrode half equations, electrode potentials here. Deduce the oxidation state of nitrogen NO3-. So let's have a look. The oxidation state of an oxygen is always a -2. That's because it's in group 6 and gains 2 electrons to fill its outer shell, so it becomes 2-. 3 2- is a 6-. Something added to 6- leaves 1- left over, so the N is in +5. NO, no charge overall, so -2 for the oxygen, something -2 leaves nothing, +2. State the weakest reducing agent in the table. So the weakest reducing agent is going to be Cl-. The reason it is, let's have a look, this equation is going to go ahead. It's got a huge +1.36 electrode potential. So this means that the Cl2 plus 2 electrons is going to form Cl-. It's definitely go ahead. Gain of electrons, oil rig, oxidation is loss, reduction is gain. So the Cl2 is gaining electrons, the Cl2 is being reduced. That's why they're sometimes called reduction potentials. The Cl2 is being reduced. It's massively being reduced. It's going to go ahead very, very readily. Cl2 going to 2Cl- because it's got a huge electrode potential here. So this is going to be readily reduced. This one, on the other hand, going the other way would be oxidized, and it's really not going to be oxidized. This Cl- is not going to be oxidized. This reaction is going to go to the right hand side. It's really not going to go to the left hand side, so this is definitely not going to be oxidized. It's not going to release electrons, so electrons is lost. It's not going to lose electrons. This Cl- is not going to lose electrons. It's not going to be oxidized, and if it's not going to be oxidized, it can't reduce something else. It's very, very poor at being oxidized, and therefore it's very, very poor at being a reducing agent, reducing something else. So it's Cl-. Write the conventional representation of a cell that has an EMF of 0.43. So I'm looking for two values that have got a difference of 0.43. I've spotted them straight away, 0.77 and 0.34. If you subtract those numbers, you end up with 0.43. So which one's going to go ahead and which one's going to be reversed? Well, the one with the larger electrode potential is going to go ahead, so Fe3 plus an electron going to Fe2 plus has got a large electrode potential of 0.77, larger than 0.34, so this one's going to be reversed. So I'm going to have Fe3 plus an electron going to Fe2 plus, and I'm going to force this one to go back in the other direction, Cu going to Cu2 plus and 2 electrons, and that will be reversed and make a minus 0.34 electrode potential. And when I add the two together, I'm going to end up with a positive value of plus 0.43. So what kind of equation have I got? I've got Fe3 plus going to Fe2 plus, and I put those on the outside. So whatever's being reduced goes on the outside of my cell. That's my reduction. And on the inside, whatever's being oxidized. So now I've got copper going to Cu2 plus, so copper going to Cu2 plus represented in the middle by this salt bridge here is what is therefore being oxidized. So whatever's been reduced on the outside and then whatever's been oxidized, the copper is forced to go to Cu2 plus to make this minus 0.34 added to the plus 0.77 to give a plus 0.43 volts overall. Use your data to identify an acid that will oxidize copper. Explain your choice of acid. Write an equation for the reaction and an EMF of the cell for the reaction. So an acid that will oxidize copper. So I've got copper here. copper being oxidized is going to go in this direction here. So when copper goes to form Cu2 plus and 2 electrons, it's going to be minus 0.34. I'm looking for another equation that's larger than 0.34, so that when we add it to minus 0.34, it gives a positive value overall. So I'm looking for something here larger than 0.34. So it's none of these three here at the bottom. They're smaller than 0.34. So it's one of these three. Which has got H plus or acid in? This one. So this one is plus 0.96. So this one's going to go ahead, plus 0.96. It's got acid in the equation. It's got nitrate ions and acid. It's nitric acid forming H plus and NO3 minus. So this is nitric acid, gives plus 0.96, and that will force the copper to be oxidized to Cu2 plus and 2 minus, minus 0.34 in the other direction, and it's going to give a value there overall of plus 0.96 minus 0.34 plus 0.62. So let's have a little look. So that's the equation, NO3 plus 4H plus 3 electrons going to NO2 and 2H2O. That's what I've picked out. It's nitric acid, this is a nitrate ion, and that's an acid, so it's HNO3 or nitric acid breaking up, dissociating, completely dissociating. It's a strong acid, completely dissociating in water to form H plus ions and nitrate ions, nitric acid. Explain your choice of acid. Well, this acid has got a value of plus 0.96, which is larger than the plus 0.34. So the copper will go backwards, go Cu to Cu2 plus and 2 electrons. It will be oxidized and give a minus 0.34, and the plus 0.96 therefore will be added to the minus 0.34 to give a positive EMF overall. So we're looking for something with a reduction potential larger than 0.34. So when it's added to minus 0.34, it gives a positive EMF overall. How are we going to balance these two equations then? Well, we know this one's going to go backwards. Cu is going to go to Cu2 plus and 2 electrons. We know that, and we know this one's going to go forwards because it's got a very, very large electrode potential. Now we've got to balance them up. So we've got two half equations. This one makes 2 electrons. This one uses up 3 electrons. So I have to multiply by 3, everything through by 3 to make 6 electrons. Multiply everything through by 2 so that this uses up 6 electrons. Add everything from the left then. 3 Cu, 2 NO3 minus, 8H plus and 6 electrons, and everything from the right, 3 Cu2 plus and 2 NO and 4 H2O, and the 6 electrons on each side, the 6 electrons on the left and the 6 electrons on the right will cancel. So that's now me putting my overall equation together from two half equations, and what's going to be the EMF of the reaction, plus 0.96 for this reaction. This one's reversed, minus 0.34 to give 0.62 volts. Question 11, probably the hardest question on the paper. This question is about compounds containing ethane diorite ions. So an ethane diorite ion is C2O4, and it's a 2 minus ion. We know it's a 2 minus ion. It shows you it here, C2O4 2 minus anyway here, and it's in this C2O4, and it's in this C2O4 as well. So we've got a white solid that's a mixture of sodium ethane dioate, which has got ethane dioate ions in it. You can see C2O4 here, and we've got a reaction involving ethane dioate ions in a minute here, C2O4. So ethane dioate ions are going to be formed from this sodium ethane dioate, and also from ethane dioic acid dihydrate, which is this, which has also got them in. So the first thing to note is that this white solid that's a mixture of sodium ethane dioate and ethane dioic acid dihydrate, which is this, and an inert solid, some other kind of impurity, has got two solids, two reactants, making ethane dioate. So the ethane dioate that we'll see in a minute has come from both sodium ethane dioate and this other thing, ethane dioic acid dihydrate. So what have we got first of all? Well, it's told us how much of this solid that is mixed in a 250 centimetre cubed of aqueous solution. And we've got a couple of titrations going on. In the first titration, 25 centimetres cubed of the solution were added to an excess of sulfuric acid, and the flask and contents were heated to 660 degrees C and then titrated with 0.02 moles solution of potassium manganate 7, when 26.5 of potassium manganate 7 have been added, the solution changed colour. So immediately I'm thinking, we've got a concentration, we've got a volume of potassium manganate 7. We should work out the number of moles. So I've got concentration is moles divided by volume. Concentration is 0.02 equals moles divided by volume. I've put the volume 26.5 centimetre cubed. I've divided by 1,000 to get into decimetre cubed. So a small unit like centimetre cubed up into a larger unit like decimetre cubed, you divide by 1,000, 0.0265. The number of moles is 0.02 multiplied by 0.0265, 0.00053. So that's the number of moles of potassium manganate 7, which is this that I'm going to react with the ethane dioate. Why have they given me this equation? They've given me this equation because it tells me 2 moles of this react with 5 moles of this. Or if I halved it, 1 mole of this would react with 2.5 moles of this. So for every 1 mole of potassium manganate 7 that I've just worked out, 2.5 moles of the ethane dioate will react. So for every 2 moles of potassium manganate 7, 5 moles of ethane dioate react. 1 mole of potassium manganate reacts with 2.5, therefore, moles of ethane dioate. So if I've got 0.00053 moles of potassium manganate 7, it must react with 2.5 times that. So 0.00553 multiplied by 2.5. I've now worked out the number of moles of ethane dioate that I've got. So where does the ethane dioate come from? Well, I've said it comes from sodium ethane dioate, and it comes from the ethane dioic acid dihydrate. It comes from both of these. So it comes from both the chemicals. So the sodium ethanoate and the ethane dioic acid together in the sample are that number of moles, because they make the ethane dioate ions between them. So the number of moles of this added to the number of moles of this, they both contribute towards making the ethane dioate ions. So the number of moles of ethane dioate ions is 0.001325. We've established that. So the number of moles of these two chemicals, the sodium ethane dioate and the ethane dioic acid dihydrate, must add up to 0.001325 together. Okay, the second titration is with sodium hydroxide. So the second titration with sodium hydroxide, I've got 25 centimetres cubed of solution. So I've got a sample of the solution titrated with 0.1 moles solution of sodium hydroxide using phenolphthalein as an indicator. The indicator changed colour after the addition of 10.45 centimetres cubed of sodium hydroxide. So I've got a concentration, I've got a volume of sodium hydroxide. It wants me to work out moles. So let's have a look. So it wants me to work out moles of sodium hydroxide. Concentration is moles divided by volume. Concentration is 0.1. I've been given that. Moles divided by the volume. Well, I've got 10.45 centimetre cubed. To get centimetre cubed up into decimetre cubed up into a larger unit value, I divide by 1,000, so that's 0.01045. Multiply the two together. 0.1 times 0.01045 is 0.001045. I know the number of moles of sodium hydroxide. Let's have a look at what the sodium hydroxide does. It reacts with this chemical, H2C2O4, which is just this one. This one hasn't got H2C2O4 in it. This one has. The ethane dioic acid dihydrate has got H2C2O4. And 2 moles of sodium hydroxide, the sodium hydroxide is making these OH- ions, 2 moles of the sodium hydroxide react with 1 mole of this ethane dioic acid. So if I've worked out the number of moles of sodium hydroxide, if I half that, divide by 2, I will work out the number of moles of ethane dioic acid that it's reacting with. So I've now worked out, because the sodium hydroxide will only react with the ethane dioic acid part, then 0.005225, in other words, this value of my sodium hydroxide divided by 2 tells me the number of moles of ethane dioic acid dihydrate in there, which equals 0.00052225 moles. So I know the total number of moles of these two chemicals added together is 0.001325. I know the number of moles of ethane dioic acid dihydrate is just 0.005225. So if I subtract the two, I end up with a number 0.008025. This must be the number of moles of sodium ethane dioate on its own. So the moles of sodium ethane dioate in the original 250 centimetre cube sample, because remember these reactions have been taking 25 centimetre cube samples out, are 250 divided by 25, which is 10. I've got 10 times the amount in the original solution. So I need to multiply by 10. I've got 0.008025 moles of sodium ethane dioate in my original solution. Now, finally, we're nearly there now. Moles equals 0.008025. We've decided that. Moles is mass divided by MR. I can work out the MR of this. 2 23s, 2 12s, and 4 16s. That's 134. So my mass of sodium ethanoate, sodium ethane dioate rather, my mass of sodium ethane dioate equals 0.008025, that's the number of moles, multiplied by the MR 134 is 1.075 grams. So that's the number of grams of sodium ethane dioate that I have in my sample. And finally it's asked me to work out the percentage by mass, so 1.075 grams out of a total mass of 1.9, because the original solid mixture contains ethane dioic acid dihydrate and another solid that we don't know what it is. So the percentage of sodium ethane dioate in there is 1.075 grams divided by the total mass of all of the solid together, multiplied by 100%, which is 56.58%. Ethane dioate ions, we know that the C2O4 2 minuses, so we know what they look like, and they look like that: C, double bond O, double bond O, O, O minus, and another O minus, and each of the O's have got a pair of electrons on them. That's what it looks like. It's probably worth remembering what an ethane dioate ion looks like. Write an equation for the reaction between iron 3 ions. So remember, iron 3 ions are going to be FeH2O6 3+. Now this is a bidentate ligand because it's got two lone pairs to donate into two covalent bonds. So it forms two covalent or coordinate bonds where the covalent bond has been formed by the donation of a pair of electrons from one of the atoms only. So it's forming two coordinate bonds or dative bonds, same thing, two coordinate bonds or two dative bonds with the Fe central metal cation in the middle. So I only need 3 of these to make 6 coordinate bonds, so I need 3 of these to replace the 6 waters, so 3 of them. How do I know it's 3 minus? Well, this is Fe3+, because waters are neutral, have no charge, they have a 0 overall oxidation state. Fe3+ in a 3 oxidation state, 3+ oxidation state, 0 leaves 3+ overall. These are 2 minuses each, and I've got 3 of them, so 2 minus multiplied by 3 is 6 minus, 3+ for the Fe, 6 minus for the 3 ethane dioate ions leaves 3 minus overall. 3+, 6 minus, 3 minus overall, and it balances. So I've got 3+ and 6 minus gives 3 minus on the left hand side and 3 minus on the right hand side, and 6 water. Suggest why the value of the enthalpy change is close to 0. It's because the number and type of bonds that I'm breaking are very similar to the number and type of bonds that I'm making. So remember, in water it's a lone pair on the oxygens of the water that bonds to the Fe in 6 coordinate bonds, and here I've got 6 coordinate bonds, albeit from 3 ligands now because they're bidentate ligands, again from the oxygen. So the same number and type of bond being broken here, broken as the waters are released, and then the same type of bonds being made and in the same number with a coordination number of 6 coordinate bonds as 3 bidentate ligands that then bond. Draw the displayed formula of ion complex produced in the reaction. So what I've got is, I've got 3 of these around a central ion. I've actually just drawn it here as a tetrahedral, an octahedral structure, but you don't really need to do that. You can just draw it flat if you want. I've got an Fe and I've got an ethane diet ion here with a bond between the Fe and the O's. So the lone pairs of electrons on the O's are going to be forming coordinate bonds with the Fe, and I've got 3 of them around it, and I've got 3 minus charge overall because the Fe is in +3 oxidation state. Each of these are in -2 oxidation state because they're -2 ions. 6 minus around from the 3 ligands, 3 plus from the Fe leaves 3 minus overall. I'm not quite sure where the 3 minus is, so I'm just going to put a square bracket and a 3 minus around, show that I know overall it's got 3 minus charge. What kind of bond angle? Well, I've got 6 bonding pairs, no lone pairs, 6 bonding pairs, no lone pairs. It's going to be an octahedral shape with a bond angle of 90. Type of isomerism, well, if you've got 3 bidentate ligands around something, it's actually optical isomerism. So you actually get enantiomers, something just to remember. Ethane diions are poisonous because they react with ions in the body. Ethane diions are present in foods such as broccoli and spinach. It's just one reason why people who eat the foods do not suffer from poisoning. Then you're just not eating enough of them. They're in small quantities.